Now that we've done the definition of a group and we've done some of the more common examples of groups, I'd like to move on and do some less common examples of groups. The very last familiar example of a group that we did is we studied the set of symmetries of a square. And we talked about how the operation there is just sort of combining symmetries of the square sequentially. Now, if you, instead of, this more advanced example of a group is, a square is just an example of a regular fourgon. So if you move up from a regular fourgon to a regular fivegon, sixgon, etc., whatever you like, the set of symmetries of a regular n-gon, let's say where n is greater than or equal to 3, so we're talking about triangles and larger, this will form a group under the combination of motions. And the notation that I use for this is I use d sub 2n. So for example, I refer to the set of symmetries of a square by d8. This is not entirely common. Some books use this notation. Maybe about half of the abstract algebra books I've seen use this notation, and about half of them will refer to the set of symmetries of a square as something like d sub 4. If I wouldn't write d sub 4, I'd write d sub 8 to refer to the set of symmetries of a square, d sub 10 to refer to the symmetries of a pentagon, etc. Another less common example, but a very good collection of examples, is to look at matrices. So the set of n by n matrices, where n is a positive integer, and we'll say with entries in a set R, this will form a group under addition if you take R to belong to either the integers modulo n for some positive integer n, for the integers themselves, the rational numbers, the real numbers, or the complex numbers. If you take your R entries to only lie in any one of these fixed sets, then the set of n by n matrices will form a group under matrix addition. And the notation that we use for this group is m sub n of R. Let's see, your identity is going to be just a big, since we're using addition here, you should be thinking of the additive identity for any one of these sets that belong to R, and this additive identity is going to be 0. So instead of being the number 0, your identity is now the 0 matrix, the matrix with all zeros as entries. And you can get away with things like associativity, since at this point in time in your life you should know that matrix addition is associative, and inverses is going to be very similar to what it was in each of these individual number systems. If I have a matrix and then I just put a negative sign in front of each one of the entries inside the matrix, then that will be the additive identity of the original matrix. Somewhat more interesting is if we take the set of n by n matrices, where n is a positive integer, that have a non-zero determinant in the set R, then this will form a group under multiplication instead of just addition if R belongs to z mod nz, the integers, the rational numbers, real numbers, or complex numbers. Now in this case, if we're talking about this set of square matrices where the operation is multiplication rather than addition, and we're talking therefore about matrices that have a non-zero determinant, then we will talk about this group and refer to it as GL sub n of R. And the GL stands for general linear group with entries in the set R. There's one more group that comes up occasionally. I didn't put it as a bullet here because I thought I'd just mention it now. It's less commonly used, but because the determinant of matrices are multiplicative, meaning that if I take two matrices A and B and I multiply them together to get a matrix AB, then the determinant of the matrix AB is equal to the product of the determinant of A with the determinant of B. If you know that fact, then you can actually show that the set of n by n matrices with determinant 1 having entries in R, where R is any one of these sets here, that itself will form a group, and that's what's known as the special linear group of dimension n with entries in R. So in the case that you're talking just about matrices, not just with a non-zero determinant, but more specifically matrices with determinant 1, where your entries lie in R, then you write SL sub n of R for special linear group. Special because it's super special, the determinant is 1. I should say that in this last example of n by n matrices, that the identity of each of these groups in GL n of r or in SL sub n of r, the identity is going to be the identity matrix, which is 1s all along that main diagonal and 0s everywhere else inside that matrix. Last but not least, let's take a look at the set 1, comma I, comma negative 1, comma negative I. This is a subset of the complex numbers, and this happens to form a group under multiplication. If I take I and I square it, right, the product of 1 with any of these things is going to be themselves. I squared is negative 1, I cubed is negative I, and I to the 4th is 1, so that's closed under multiplication. Negative 1 times any of these four things is very clearly in the set, and I, which is negative 1 times I mean, you can just go through and check sort of pairwise, or by making a Cayley table, which is probably a better thing to do, that when you combine any of these two things under multiplication, you're going to get something else in this set. You're using multiplication, good old multiplication from the complex numbers, which happens to be an associative operation. Therefore, the 1, which is the identity of the complex numbers, is the identity of this group as well. And you've got inverses as well, which is something that you could also check from creating a Cayley table for this particular set. I suppose not last. Not last and not least, now last but not least, is if you take the set of bijective functions from a finite set to itself. So by bijective, in case you're unfamiliar, I mean the set of functions that are both one-to-one and onto. I use the word bijective for that. So the set of bijective functions from a finite set to itself is a group where your operation is function composition. Something that will be very important to us as we progress in abstract algebra is that if n happens to be the size of this finite set, okay, then this set of bijective functions from a set of size n to itself under function composition is denoted by S sub n. It's called the symmetric group on n letters, so S for symmetric group. What is going to be your identity function? Since this is kind of a different example, let's talk about that. Well, closure is if you take two bijective functions with domain and range that are equal and you compose them, you're going to get another bijective function with equal domain and range. So we've got closure. Associativity is annoying, but is something that maybe was done in a high school algebra class, or perhaps a pre-calculus class. At some point in time, I assume that was covered, that function composition is associative. If not, it wouldn't be the end of the world if you did it yourself, proved that. The identity function, if you're talking about the identity, you're talking about the identity function. That is the function that takes every element of the set and just sends it to itself. If you were graphing on a plane, you'd think of this as the function y is equal to x. That's your identity function. The output is just the same as what the input is. That's how I read that in a more abstract algebra way. And inverses, I love these little pictures. For instance, Gallian does in his book. He'll just draw a big oval and he'll put n dots inside of it. Then he'll draw another oval and put n dots inside of it, and he'll just draw arrows. So this element goes here, this element goes here. Yeah. Arrow from the oval on the left to the oval on the right, telling you where each one of the dots inside goes with an arrow. The inverse of that function would just be follow the arrows backwards. So follow the arrows from the right to the left instead of the left to the right, and you'll have the inverse of that function. That is, whatever you send an element x to, if x gets sent to y, then the inverse function is going to send the element y to the element x, and that will result, if you do that function composition, that will result in your identity function, which takes an element from the set to itself, which pictorially would just be a picture of all n things inside your big oval, just having straight lines, straight horizontal lines going straight across. One more example for now. Another important example that we'll generalize in the next video. Let's show that the set of positive integers relatively prime to the number 14 and also less than or equal to 14 is a group under the operation of modular multiplication. So So this is going back a little ways. The way that I'm going to prove this is a method of proof that's only going to really work for finite groups. And there are plenty of infinite groups. Most of our familiar examples are infinite. But let's do an example with finite groups here to just cover all of these properties that we're looking for in the definition of a group. So first of all, let's find the set of positive integers relatively prime to 14 and less than or equal to 14. And let's denote that set by u of 14, u parentheses 14, end parentheses. The u stands for units, which is something that if you do continue on in abstract algebra, you should hopefully study when you get to the study of what's called a ring. So u of 14, set of integers less than or equal to 14, positive integers less than or equal to 14, relatively prime to 14. So I've got to get rid of all the even integers, and then I've also got to get rid of 7. So when I look at that list, I end up with 1, 3, 5, 9, 11, and 13. Now what I can do is I can make a Cayley table for this group, which means that what I have here is, as the rows are all indexed by an element of this set, the columns here are all indexed by an element of this set, and what I write at the entry of a particular row and column is the output under this operation when I combine these two things. First doing the operation in the row, and then second doing the operation provided combining with the elements that's indexing the column. So for instance, when I come down here to this third row, which is indexed by the number 5, and then I go over 2 columns. So I look at the entry in row indexed by 5, column entry 3. What I put here is the result 5 times 3. What I put in 3 times 5 would be sitting here with 3 first and then the 5 second. Now what's going on here with the Cayley table? When I take 1, 1 is my identity of this particular group, so when I take 1 and I multiply it by anything, I just get that same output back. So that fills in this row and this column for me. It doesn't matter the order. 1 times 3 or 3 times 1 is still just 3. So that's how I see these rows and columns getting filled in. 3 times 3 is 9, so filling in this 9 right here is really very easy. It's when I get to 3 times 5 that maybe something interesting happens. So I take the 3 and I compute 3 times 5, and what I actually get is the number 15. But what I'm working with here is modular multiplication. So instead of writing down 15, which isn't in my set of numbers, what I'm going to write down is the number that results when I take 15 and I associate it with its remainder when I divide by 14. So 15 is 1 times 14 plus 1. So when I take 15 and I divide by 14, my remainder is 1. So instead of putting a 15 right here in the 3, 5 entry, I put the number 1 instead. Similarly here, we don't really need to go through every entry that's inside this table, but if I take, I'll do 3 and 11 because it's a little bit nicer. When I take 3 and I multiply by 11, I get 33, which is definitely not 5. But the thing to remember is that 33 is 5 more than 28, which is my next highest multiple of 14. So 14 times 2 is 28, and 33 is 5 more than that. So I associate the number 13 with the number 5, and I put a 5 right here. In that manner, I can fill out this entire table. And so you notice that I have really proven closure by completing this table, because I took, I have all possibilities for any 2 members of this set U of 14. Any way that I could have combined 2 of these entries is some sort of entry inside the table, the row and the column. And no matter which entry I picked, I have a number here, and it's one of the following numbers, 1, 3, 5, 9, 11, and 13. So I've shown closure by showing that I could complete a Cayley table, and the entries inside the Cayley table all came from my original list. I've also shown that there's a multiplicative identity, which is right here and here. That is, I found a row where the entry inside, all the way as I read across that row, was the same as the column. And similarly, I found a column where the entry, as I read down that single column, was exactly the number that came from the row. So that's showing that I have this row and this column that I've got a multiplicative, or I have an identity under my binary operation. I've also shown that inverses exist, and I've shown that because there's a 1 inside every row and column, which means that if I were looking for the inverse of the number 11 under this operation, I would go down to the 11 and I would read along the line until I find the 1. Where I find the 1, which happens to be my identity, I say, what column are you in? Entry number 1 inside this row. I'm in the column of 9. And so that what that means, if I take 11 and I multiply it by 9, I should be getting something that has a remainder of 1 when I divide by 14. So 9 times 11 is 99, and 98 apparently is a multiple of 14. So that has shown that we've satisfied all of the group operations. I mean, we haven't checked associativity fairly enough, but associativity, that is the one thing you can't check from a Cayley table, but multiplication, even modular multiplication, is associative, and that's the last of our group requirements. The last thing I'll say is this, although it is not a requirement of a group, sometimes you have a commutative operation or an abelian group, and that means that it doesn't matter the order in which you combine the elements of the operation. This is something that we know about multiplication and about addition on common number systems, is it doesn't matter the order in which you add things, and it doesn't matter the order in which you multiply things. Addition and multiplication are commutative operations for our normal number systems. This is true when you add in this modular requirement. That's something that we studied when we studied properties of modular arithmetic. And so we actually do have a commutative operation here. The way that you can see that from a Cayley table is if you take a look at this diagonal. If you organize things so that they go in the same order inside this Cayley table, and you look at this diagonal here, the Cayley table is symmetric about the diagonal. Okay? Meaning that if I drew in a nice line going through these guys right here, I have symmetry going across that line. Okay? And you can see it. 3, 3, 5, 9, 5, 9, 1, 1, 9, 11, 13, 11, 13, 11. I have this symmetry reading across this line, and that means that I have a commutative operation. So that's another way that we could tell from the Cayley table that I do actually have this additional requirement, and it works both ways. If I found that there was a place, any old place in the world in the Cayley table, and what I had was not symmetric about that line, then I would not have an abelian group. So this can be identified from a Cayley table, which is why it makes it a very nice, powerful, and useful tool when studying finite groups.